get started. Because sooner we get through things, sooner we'll be done. So, homework number 3 on chapter 4 is due today on on the homework site. Homework number 4 on chapter 5 will be due next week on Wednesday. Homework number 5 on chapter 6 will be due on the 8th. So that's 2 weeks from now. Also, that will be when we're having our first exam on chapters 1 through 6. We will be having a lab today. So, finishing off chapter 5 and starting up chapter 6. The last part of chapter 5 is normal forces. The normal force is the force exerted by a surface on an object. It's always perpendicular to the surface, which is why it is called the normal force. And it is always as big as it needs to be to keep the object from passing through the surface. So basically, the normal force will always be whatever it needs to be to set the net force perpendicular to the surface equal to 0. So if you just have like a can of tomatoes on a surface, it's going to push down with its weight. And the normal force is equal to the weight and in the opposite direction, making the total force vertically equal to 0. Now, if you're also pulling up on the object, like we see here, the normal force will be a bit less because the total force in the y direction has to be 0. And there's some force in the y direction from the upward pull of the force. So the normal force can be equal to, greater than, or less than the weight. So here with this book on the table, the normal force on it is equal to its weight. If I push down on the book, normal force will be greater than the weight. If I lift up on the book, normal force will be less than the weight. And it is always perpendicular to the surface, which means it may not be vertical. And often when the surface is tilted, like in this example, it is easier to tilt the axes and set the y-axis to be perpendicular to the surface than keep the y-axis vertically. Makes the problems easier because you know that the normal force will cancel out in that direction, and it's easier to figure out what it's going to be given that situation. So here we have a problem about normal force. So the general idea is that the normal force will be whatever needs to be to cancel out all the forces pushing into the table. So here we have a 4.53 kilogram holiday turkey. It's moved towards the center of a smooth table by 2 people at a feast. Person 1 is exerting a force with a magnitude of 35.5 newtons downwards at an angle of 34.6 degrees below the horizontal, as shown in the sketch. Person 2 is exerting a force of 2 with a magnitude of 39.7 newtons at an angle of 21.2 degrees above the horizontal. So what is the magnitude of the normal force exerted by the table on the turkey? So the general idea here is that we know the turkey is not moving up or down. So we know the sum of all the forces in the y direction will equal 0. And we need to just solve for what the normal force will be. So I can get started showing you how this process works. So for this problem, the way you'd approach it, you can list out what you know. Your first force is 35.5 newtons. It's 34.6 degrees below the horizontal. So the angle could be thought of as negative 34.6 degrees. Your second force is 39.7 newtons. It is 21.2 degrees above the horizontal, so it is positive. The mass of the turkey is 4.53 kilograms. G is 9.81 meters per second squared. No, and can I make this? Oh, wait. No. I'll stick it over there. And we're looking for the normal force. So our basic assumption when we're looking for normal force is that all the forces perpendicular to the surface will add up to 0. So the sum of all the forces in y is going to add up to 0. So that's going to be force 1 y plus force 2 y minus, well, okay, that probably could be written as plus. What happened? Yeah. Oh. Stop sharing. Sorry. Can I make this? No, just shrink it down. Plus weight in the y direction plus normal force in the y direction. That all equals 0. So if we write these out, force 1y is force 1 times sine theta 1. Force 2y is force 2 times sine of theta 2. The weight in the y direction is going to be negative mg because it's pointing directly down. The normal force in the y direction is just going to be normal force plus positive normal force. So if we solve for normal force, we get normal force is equal to mg minus f1 sine 1 minus f2 sine 2, sine theta 2. So that's 4.53 kilograms times 9.81 meters per second. That's the weight of the turkey. Minus 35.5 newtons times the sine of negative 34.6 degrees. This is going to be a negative number. So that's the pushing down. And then minus 37.9 newtons times sine of 21.2 degrees. It's going to be a positive number pulling up. So the weight is 44 newtons. We're going to add another 20.2 newtons because we're pushing down with 20.2 newtons from force 1. And then we're going to subtract 14.4 newtons because we're pulling up with 14.4 newtons with force 2. And that gives us a normal force of 50.2 newtons. Any questions about normal force? Now here is a situation with normal force on a slope. So this is asking if you have a child of mass m that rides a toboggan down a slick ice-covered hill that is inclined Unica at an angle theta with respect to the horizontal, and you want to figure out the acceleration of the child and the normal force exerted on the child by the toboggan. So since this is all figurative, the trick here is we're going to work this out in a coordinate system. So this is how you solve problems on a slope. You work it out in a coordinate system that is tied to the slope and not to verticality. So you set y is perpendicular to the slope and x is up along the slope. That makes it easier to solve these problems because you usually know what the weight is. So you can break the weight into x and y components compared to the slope, and that'll let you find out what the normal force is and what the force is along the slope are. So if you have a toboggan on a slope like this, your weight is mg, your acceleration is what you're looking for. And to figure that out, you need to know what the normal force is at some level. You can sort of figure it out without knowing what the normal force is, but this is actually also asking for the normal force. So the sum of the forces equals mass times acceleration. We know this toboggan is traveling in the x direction, down the slope. So the sum of all the forces in the y direction is equal to 0. That means the sum of all the forces in the x direction just equals mass times acceleration. We're not worrying about the direction there. We're just talking about the size of the acceleration. So the sum of all the forces in the x direction is the x component of the weight plus the x component of the normal force. Those are the only two forces acting on this toboggan, because we haven't discussed friction yet. That's next chapter. So to find out what the weight is and what the normal force is, well, the x component of the weight, the x component of the normal force is 0, because that normal force is perpendicular to the slope. So it has no component down the slope. So the weight, the x component of the weight will just equal mass times acceleration. The weight times the sine of the angle of the slope equals mass times acceleration. That is because this angle here is the angle of the slope. For a little bit of geometry, you can figure out that it is the same as this angle here between the vertical and the weight downwards. How can we get this out? We have the horizontal. Then we continue the slope. This angle theta. This is a right angle. This is a right angle. So this is 90 minus theta, and this is theta. So knowing that, given that this angle here is the same as the angle of the slope, the component down the slope ends up being weight times sine theta, and the component into the slope is negative weight cosine theta. So Wy is negative weight cosine theta, Wx is weight sine theta. And weight sine theta is going to be mass times acceleration, but weight is, so acceleration is weight times sine theta over mass, but weight is mg. So we can cancel out the mass, and the acceleration will end up being just g sine theta. So basically, inclined planes slow down acceleration. If you were vertical, you'd have acceleration of g. If you're at 30 degrees, you'll have an acceleration of half of g, because the sine of 30 degrees is 0.5. So, you figure out the component down the slope from gravity, and that's what's accelerating you down the slope. You want to also figure out the normal force. Well, all the forces in the y direction equal 0. So weight in the y direction plus normal force in the y direction equals 0. So that's minus weight cosine theta plus normal force equals 0. So normal force is going to equal weight cosine theta. So normal force equals mg cosine theta. And this setup where normal force equals mg cosine theta and the force from gravity down the slope is mg sine theta is fairly common. Because if you just have a thing on a slope, on an incline, that's what you get. Any questions? Okay. So that's the end of normal forces in chapter 5. They'll come up again in chapter 6. So a force is a push or a pull. Mass is a measurement of the difficulty in accelerating an object. Newton's first law is if the net force on an object is 0, its velocity is constant. An inertial frame of reference is one in which the first law holds. Newton's second law is that the sum of all the forces on an object equal its mass times its acceleration. A free body diagram is a sketch showing all the forces on an object, just putting them around a single point, so it's easier to work out the details. Newton's third law is that if object 1 exerts a force F on object 2 will exert a force minus F on object 1. You get forces equal in size and in the opposite direction to each other. These are called action-reaction pairs. Contact forces are an action-reaction pair of forces produced by two objects in physical contact. So Newton's third law says that all forces come in pairs. They're action-reaction pairs. So for any force, there will be a reaction pair to it, partner to it. So you're being pulled down by gravity by the Earth. You're actually pulling the Earth up by your gravity with an equal force in the opposite direction. But the Earth is so much more massive than you, it has no real acceleration. Forces are vectors. You can break them into their components to work with them. You can apply Newton's laws to each component of the forces independently. Weight is the gravitational force exerted by Earth on an object. On the surface of the Earth, weight is mass times g. Apparent weight is the force felt from contact with the floor or scale. It changes when you're in an accelerating reference frame. Normal force is the force exerted perpendicular to a surface by that surface. And normal force may be equal to, lesser than, or greater than the object's weight. And we use normal forces to do things all the time. Because it turns out normal forces are closely tied with friction. And so when we want friction to happen, we add normal forces. So let's go on to chapter 6, the applications of Newton's laws. So we're going to talk about specific cases of forces and cause and effect. So we'll talk about things like tension in cables and wires and ropes, and forces ending up like that. We'll also talk about friction and other situations. So we'll start by talking about frictional forces. Then we will move on to strings and springs and start covering some of the stuff we actually been doing in labs. Then we'll talk about translational equilibrium. Which is a subset of the more general static equilibrium, which you can really go hog wild for. There's a whole engineering course called statics. Then we'll talk about connected objects. So how to treat objects, how to deal with objects that are connected in some way, and ways to treat them as a whole system or to make the math easier and things. And then lastly, we'll talk about circular motion. So, friction has its basis in surfaces that are not completely smooth. No two surfaces are perfectly smooth. So on a microscopic scale, even a smooth surface is rough. It's jagged. And this means that if you have two surfaces in contact with each other, they interact, and this leads to a force of friction that tries to keep these two objects from sliding relative to each other. And because these surfaces are not smooth, it turns out the strength of this friction force is based on how hard they're being pushed together. The harder you push them together, it turns out the stronger the friction force is. So the classic example is like if there were slopes, the harder they're pushed together, the harder it is to move the slopes around. Turns out that's not quite what actually happens. I seem to recall, actually they get more contact the harder you push them together. Oh, oops. I thought I'd fix this, but I missed it. Sorry about that. Thought I'd gone through and caught that. So, kinetic friction is the friction experienced by surfaces that are sliding against one another. The kinetic frictional force depends on the normal force. So, this book, like many things, uses a lowercase f for friction. So, kinetic friction is simple and straightforward. The kinetic frictional force is mu kinetic times the normal force. Mu kinetic is the coefficient of kinetic friction. The coefficient of friction, that is something that is determined experimentally. You look it up, or it'll be given in problems, or you'll be asked to find it. You're never going to be expected to memorize coefficients of kinetic friction. And you multiply that by the normal force to find out the force of friction. And kinetic friction will always point opposite the direction of the sliding. It's trying to cause the two surfaces to not be sliding against each other. So usually it points opposite the direction of motion. There are some exceptions, but usually it points, if you're moving along and you come to a sliding stop, which I cannot do because I have too much friction on my shoes, the force will point opposite the direction you're moving as you slow down. And there's another type of friction, static friction. It also has a coefficient. Coefficients of friction, because they convert forces to forces. So normal force is a force, friction force is a force. These are unitless. They're just numbers without units. So, some examples. Rubber on concrete, dry, the coefficient of kinetic friction is about 0.8. The coefficient of static friction is 1 to 4. Steel on steel, kinetic friction is about 0.57. Static friction is 0.74. You'll notice the static friction values are all bigger than the kinetic friction values. Glass on glass, 0.4 for kinetic, 0.94 for static. Wood on leather, 0.4 for kinetic, 0.5 for static. Copper on steel, 0.36 for kinetic, 0.53 for static. Rubber on concrete when wet, 0.25 for kinetic, 0.3 for static. Steel on ice, 0.06 for kinetic, 0.1 for static. Wax ski on snow, 0.05 for kinetic, 0.1 for static. Teflon on Teflon, 0.04 and 0.04. Teflon's really slippery, so the difference between static and kinetic is pretty small. And then synovial joints in humans are 0.003 for kinetic and 0.01 for static, because they're very well lubricated. This is on the same scale as lubricated ball bearings. So kinetic frictional force is also, it turns out, independent of the relative speed. It doesn't matter how fast you're going. The friction force for sliding will be the same. It also turns out doesn't matter how big the area of contact is. This sort of makes sense because the larger the area, you get more friction, but the larger the area, the less pressure you're applying. So the two surfaces aren't quite squished together as hard. So that effect is independent. So it's real nice and simple. So if you put a second block on top of your first block, you double your mass, you double your normal force. You know, double your mass, you double your weight, you double your normal force, you double your friction. So this is kinetic friction. It acts to keep you from sliding away. Static friction, on the other hand, tries to keep an object from starting to slide. So it is harder to get something started than to keep it moving. You know, it's harder to unstick something than to keep it going. So it keeps an object from starting to move when a force is applied. And the static frictional force is like the normal force. It is whatever it needs to be to keep the movement, you know, the net force zero. It's one of those forces that counteracts things. So if I push on this book, the static friction it generates will get more as I push harder until it reaches a maximum. And then the book will start to slide. So as I push, I'm pushing harder and static friction goes up and up and up, and then eventually it starts to slide. And that's when I overcome the maximum. So for static friction, the maximum is mu static times the normal force. So the static friction will be anywhere between 0 and the maximum. It'll try and be as big as it can be. You know, it'll be as big as it needs to be, but there is a cap. Usually problems are interested in the point where you overcome it. Just, but it's also independent of the area of contact and the relative speed of the surfaces. Well, the relative speed of the surfaces when it comes to static friction is always 0. So, yeah. So here, someone at the other end of the table asks you to pass the salt and feeling quite dashing. You slide the 50-gram salt shaker in that direction, giving it an initial speed of 1.15 meters per second. If the shaker comes to rest with constant acceleration in 0.840 meters, what is the coefficient of kinetic friction between the shaker and the table? So the useful equation here that you might need is that, you know, velocity squared is initial velocity squared plus 2 times acceleration times delta x. And then how much time is required for the shaker to come to rest if you slide it with an initial speed of 1.32 meters per second. So at this point, you'll know the acceleration because you'll have found it when you're finding the friction, and you can use that to figure out for part B. I'll give you a few minutes to work on this, and then I'll go through it. So go over what we started with. Our mass, 0.05 kilograms. G is 9.81 meters per second squared. Our initial velocity is 1.15 meters per second. Our final velocity is 0. Our delta x is 0.84 meters. We want to find mu kinetic. To find mu kinetic, we're going to need to know the normal force, the kinetic friction, and the acceleration. So we'll find the acceleration, then the kinetic friction force, then the normal force, then mu kinetic. So v squared equals v naught squared plus 2a delta x. So acceleration is v squared minus v naught squared over 2 delta x. So 0 squared minus 1.15 meters per second squared over 2 times 0.84 meters, which gives us an acceleration of minus 0.787 meters per second squared. We also know that minus force kinetic, because it's in the opposite direction to the motion. So the kinetic force is pointing in the negative x direction and we're moving in the positive x direction, is equal to mass times acceleration. So force kinetic is going to be minus mass times acceleration. Oh, wow. Also, we can also figure out the normal force. So the forces in the y direction equal 0. So normal force minus weight equals 0. The normal force equals the weight, which equals mg. The kinetic force equals mu kinetic times the normal force, which equals minus mass times acceleration. Mu kinetic equals minus mass times acceleration over the normal force. The mu kinetic equals minus mass times acceleration over mg, or minus acceleration over g. So minus 0.787 meters per second squared over 9.81 meters per second squared. Mu kinetic is 0.0802. And there are no units on coefficient of friction. We want to figure out how long it takes for the shaker to come to rest if we started with an initial speed of 1.32 meters per second. So we want to find time when initial velocity is 1.32 meters per second. Well, velocity is initial velocity plus acceleration times time. So time is velocity minus initial velocity over acceleration. So 0 minus 1.32 meters per second divided by 0.787 meters per second squared is 1.68 seconds. And I saw I had an animation order mistake. So let me fix that real quick. 1, 2. Yeah. Everybody got this? Any questions? I will continue. Here we have another kinetic friction problem. We have a sea lion that slides from rest with a constant acceleration down a 3-meter long ramp into a pool of water. If the ramp is inclined at an angle of 23 degrees above the horizontal, and the coefficient of kinetic friction between the sea lion and the ramp is 0.26, how much time does it take for the sea lion to make a splash in the pool? So here we'll be using Now x equals x naught plus v naught x t plus 1/2 acceleration x t squared. But now x naught will equal 0 and v naught x will equal 0. So these two terms will go away. Okay. And here we're going to again put ourselves in the reference frame of the slope. So we're tilting our axes. And we have a slope at an angle theta. So again, we have mg sine theta pointing down the slope, and mg cosine theta, the component of the weight pointing into the slope, is mg cosine theta. And then friction is pointing away and normal force is pointing out of the slope. So I'll give you guys a few minutes to work on this. So things we know. G is 9.81 meters per second squared. Our initial velocity is 0. The slope is at an angle of 23 degrees. Delta x is 3 meters. We're traveling 3 meters down the slope. Mu kinetic is 0.26. We don't actually know the mass, but it turns out it cancels out, so it's not important. And we're trying to find time. So to do this, we'll need to know the normal force, the kinetic friction, and the acceleration. We know the x component of the normal force is 0. We know the y component of the normal force is n. We know the force, the kinetic, the x component of friction is minus kinetic friction. The y component of friction is 0. The x component of the weight is mg sine theta, and the y component of the weight is negative mg cosine theta. We break it down into we break every force down into their components. Then we can start with the sum of all the forces in the y direction, which is mass times acceleration in the y direction, which is 0 in this case. because again, y is perpendicular to the slope, and you're sliding down the slope. There's no movement in the y direction. The normal force minus mg cosine theta equals 0. The normal force equals mg cosine theta. Now, we can use our formula for kinetic friction to find kinetic friction. So our forces in the x direction is mg sine theta minus kinetic friction. So mg sine theta minus mu kinetic times the normal force. So mg sine theta times mu kinetic mg cosine theta. And that equals mass times acceleration in the x direction. So this is all the forces in the x direction. It's mg sine theta from gravity down the slope minus mu kinetic mg cosine theta from kinetic friction pointing up the front slope. And that equals mass times acceleration. So one thing you might see is all of these terms have a mass in them. So if we want to find acceleration, we can divide everything by mass, and we get g acceleration in the x direction is g sine theta minus mu kinetic g cosine theta. So g times sine theta minus mu kinetic cosine theta. So 9.81 meters per second squared times the sine of 23 degrees minus 0.26 times the cosine of 23 degrees. And that comes out to 1.5 meters per second squared. And now that we know the acceleration, 1.5 meters per second squared, well, x equals x naught plus v naught xt plus 1/2 acceleration x t squared. X naught is 0, v naught x is 0, so delta x is 1/2 acceleration x t squared. So t is square root of 2 times delta x over acceleration x. So that's the square root of 2 times 3 meters divided by 1.5 meters per second squared. I made a typo on that. I'll fix it. And that comes out to 2 seconds. I'm going to fix that typo real quick. Meters per second square space up. There. That didn't work the way I wanted it to. Okay, well, there. Hoping for a shortcut, didn't get a shortcut. So this is a bit got a bit long, but it's not that complicated. The basic idea is that friction on a slope is usually mu kinetic times mg cosine theta. And then you can work out what the force down the slope is. So those were kinetic friction problems. Here's a static friction problem. This is actually an example of how you test for static friction. This here is a device you would use to test static friction, more or less. So you put something on here and you tilt it up until it begins sliding. And then you can work out the static friction between the object and the surface from the angle. So that is what this problem is about. A flat bug truck slowly lifts its bed upwards to dispose of a 95-kilogram crate. For small angles of tilt, the crate stays put, but when the tilt angle hits 23.2 degrees, the crate begins to slide. So what is the coefficient of static friction between the bed of the truck and the crate? So at 23.2 degrees, your static friction is equal to your maximum static friction. So if you solve everything assuming nothing is moving, that's going to be your max. And you can use that to figure out what the coefficient of static friction is. And yeah, it really just depends on the angle. Well, and the two surfaces, but I'll give you a little while to work on that. Now, once again, the force of gravity down the slope is mg sine theta. The force of gravity into the slope is mg cosine theta. And now the force of static friction is going to be equal to mg sine theta. They're going to cancel each other out exactly. So here's the situation we have. When you have G is 9.81 meters per second squared, mass is 95 kilograms, the angle is 23.3 degrees. We want to find the coefficient of static friction. So we'll need to figure out the normal force and the force of static friction. Nothing is moving. So the normal force in the x direction is 0. The normal force in the y direction is n. The force of static friction in the x direction is minus force of static max, because we're right at the point where it starts sliding. The force of static friction in the y direction is 0. Weight in the x direction is mg sine theta. Weight in the y direction is negative mg cosine theta. So let's start with the y direction. We know the sum of all the forces in the y direction is equal to 0, because nothing's moving. So normal force minus mg cosine theta equals 0. Normal force equals mg cosine theta. Now we can look at the forces in the x direction. They also add up to 0. So weight x plus force static x plus normal force x equals 0. So mg sine theta minus F static max equals 0 equals 0. F static max is mu static times the normal force. And so that's going to be mu static times mg cosine theta. That equals 0. So let's solve for mu static. Mg sine theta equals mu static mg cosine theta. We'll divide both sides by mg cosine theta. Mu static is mg sine theta over mg cosine theta. Mg cancels. Blue marker over here. So mg in both cases cancel. And you get sine theta over cosine theta, which is the tangent of theta. So it turns out mu static will be the tangent of 23.3 degrees. So you can literally just measure the angle at which something starts to slide, take its tangent, and that will be the coefficient of static friction for those two surfaces. And that's how you experimentally determine the coefficient of static friction. So the tangent of 23.3 degrees is 0.429. And it's just a number. Coefficients of friction are always just numbers because they convert force to force. Any questions about that? There's that nice thing where gravity cancels out. Everybody okay with me going on? So here we have a car driving with its tires rolling freely. They're just going along. Nothing weird is happening. You're driving like you normally would. Is the friction between the tires and the road static friction or kinetic friction? And a helpful thing to think about is, what would be going on if you had a wheel that was made of a bunch of feet, a bunch of shoes as it rolled? Because when you walk, your feet don't move with respect to the ground. So that's clearly static friction. So when a car drives along the road, do you think it's static friction or kinetic friction? Under normal circumstances. You're not doing things like burnouts. So the best idea is to think about what is happening right at the contact point between the tire and the road. Are they actually moving relative to each other? So, who thinks it's static friction between the road and the tires? Who thinks it's kinetic? While the car is moving, when you have something rolling, let me see if I can find something round. That'll work. When you have something rolling, as it rolls, the point of contact doesn't move relative to the surface. You just have the next bit of the ball move down into contact. So the point where it's touching is always not moving. And so you have static friction. Well, unless, when you don't have static friction, that is a bad thing, usually. So that's, if you've been in a car and you skid out, that's when you're on static friction. You have less control because you have less force from your tires. Or a burnout, where you're spinning the wheels really fast and they're not actually pushing you. So also drifting is a controlled case of failure of friction. So the contact point between the road and the tire doesn't actually slide. The friction is static under normal circumstances. It can definitely be kinetic, but that's usually bad. So that was friction. Now we have strings and springs. Strings have tension. So if I have a rope, it has tension in the rope. We talked about the rope having tension. It transfers force along the length of the rope. Tension pulls towards the middle of the rope. It always pulls in. It doesn't push out. I can't push with a rope, but I can pull with a rope. And the tension will be, under ideal circumstances, the same everywhere throughout the rope. So the rope is pulling towards the middle. So you're pulling on each end with the tension. The rope is pulling back on you towards the middle with the tension. And at any point along, there'll be the same tension. So along a string, the tension will always be the same. So in a real rope, like if I take this rope and I hang a weight from it, this actually does have tension that varies throughout the rope because the rope has some weight. So up here, this rope is holding up more than down here. But for an ideal rope that doesn't have any weight, tension will be continuous throughout. So if you have a massless rope, which we're going to assume all our ropes are massless, tension will be constant throughout. So this is a useful thing. And these strings and ropes can transfer force. And we can have machines that help redirect that force. It's called a pulley. Pulleys redirect tension. An ideal pulley is one that simply changes the direction of tension. We're going to deal with ideal pulleys. So the tension in an ideal rope has the same magnitude everywhere, and a pulley just changes the direction in which it acts. So if you have a single pulley, it allows you to pull downwards to create a tension force that lifts upwards. That is helpful. Turns out if you have more pulleys, you can pull downwards to get a bigger force with like a block and tackle. But it's all just redirecting the tension. So here we have a traction device that employs 3 pulleys. It's applied to a broken leg, as shown in this sketch. So the tension will be the same everywhere throughout this rope. So you can figure out the tension by thinking about what's going on with this mass down at the bottom. So the middle pulley is attached to the sole of the foot, and a mass M supplies the tension in the ropes. So we have T1, which is up at 40 degrees, and T2, which is down at 40 degrees from the horizontal. And we want to find the value of mass M if the force exerted on the sole of the foot by the middle pulley adds up to a total of 165 newtons. So you can see the vertical components. For T1, it's T times sine of 40 degrees up. For T2, it's T times sine of 40 degrees down. You can see how, because these angles are the same, the vertical components of the force will cancel out. And so the force will be entirely horizontal. And it'll be T cosine 40 degrees plus T cosine 40 degrees. And that's being provided down here, where that tension is providing enough force to lift this mass M, so the tension in the rope will be mg. So I'll give you another minute or so to work on this. So the way you can approach this, G is 9.81. The sum of all the forces in the x direction is going to be 165 newtons. The two angles are both 40 degrees. We don't know what the mass is. We don't know what the tension is. But we can find the tension by looking at the forces in the x direction. So the sum of all the forces in the x direction is 165 newtons. Tension 1x is T cosine theta 1. Tension 2x is T cosine theta 2. T cosine theta 1 plus T cosine theta 2 is 165 newtons. That's tension times the cosine of 40 degrees plus tension times the cosine of 40 degrees. So 2 times tension times the cosine of 40 degrees gives us 165 newtons. The tension is going to be 165 newtons divided by 2 times the cosine of 40 degrees, which is 107.7 newtons. If we also look at the forces down here, we'll see that 0, the forces here, 0 is equal to tension minus mg. These are the forces around the mass. So tension equals mg. So mass is going to be tension over g. So 107.7 newtons over 9.81 meters per second squared is 11 kilograms. So here we have a vertical scale. Here, if you hang a mass on the scale, it measures the tension, and that is, this would be 9.81 newtons. Now here, if we hang a mass on each side of a scale with the scale horizontal in the middle, will the reading on this horizontal scale be greater than, less than, or equal to 9.81 newtons? So this is effectively reading the tension in the row. So what do you think that will be in this case here? Is this going to be more than 9.81 newtons? More than if it's just hanging vertically? The same or less? Who thinks this will be more? Got weights on both sides, as opposed to this one, which is equivalent. You think this will be more? Who thinks it'll be the same? Okay. Who thinks it'll be less? Well, the people who answered are correct. So if we look right here, 0 equals tension minus mg, tension equals mg, which is 9.81 newtons. This will have the same tension on both sides, because this applies to either here or here. So it will be equal to 9.81 newtons. It'll be the same. We have a bit more time. Let's do a few more. Let's talk about springs. So strings have a tension. Springs have an effect where the force increases with the amount the spring is stretched or compressed. And that force is usually written, the force law is usually written, this is the force applied to the spring, but the force from the spring is usually minus kx. So this textbook is a little funny, drop the minus sign, but basically, if you stretch or compress a spring, it will have a force equal to, it will oppose that motion with a force of minus kx. This is the force you have to apply. So this is the applied force, it's kx. If you do it with vectors, you get minus kx. K is called the spring constant. It is how strong, a measure of how strong the spring is. The bigger the spring constant, the stiffer the spring. So here we have a spring device that acts to improve airflow through nasal passages. It's called the nasal strip. It consists of two flat polyester springs that are enclosed by an adhesive tape covering. And measurements show that a nasal strip can exert an outward force of 0.22 newtons on the nose, causing it to expand by 3.6 millimeters. If this was an ideal spring, let's find its force constant in newtons per meter. The units for K are newtons per meter, like we've been doing in labs. And how much force would be required to expand the nose by 4.1 millimeters. So we have a bit of a limited amount of time, so I'll just go through this. So what do we know? The force is 0.22 newtons. Our X is 3.6 millimeters. We're interested in K. We're really only interested in the magnitudes here, so the sign doesn't matter. And for B, we want to know if X2 equals 4.1 millimeters, what is K? What is the force? So force equals Kx. K is going to be force over X. For 0.22 newtons over 3.6 times 10 to the minus 3 meters. But note that is millimeters. So K is 61 newtons per meter. And then force is equal to Kx. So if X is 4.1 millimeters, force is 61 newtons per meter, times 4.1 times 10 to the minus 3 meters. The force is 0.25 newtons. And I think we will stop there for today. That was springs. The next section is translational equilibrium. Where if nothing is moving, the sum of all the forces is 0. You can use this to figure out unknown forces, like we were doing with the box on a slope kind of thing. So we're going to stop there for today, and then we'll have the lab. We're going to stop sharing. I'm going to end.